Yay!
Yay! Okay, here's how we can use Gauss's law to figure out what's happening inside of conductors. This is sort of it can be confusing, but a really interesting property of conductors with cavities inside of them. Okay, so let's suppose I have this conductor, and it's a thick conductor, but it's got a hollow center. It turns out not to be important that the middle is hollow with a spherical shape, but that just makes it easy to see right now. But it could be any shape. It could be an arbitrary shape. But anyway, so suppose I got this conductor. So the conductor has an inner radius R1, and outer radius R2. So it's sort of a ball with a hollow spot in the middle. And then the charge, the surface charge density is 6.37. That's a curious number, but it makes things work out kind of nice. Microcoulombs per square meter. Okay, so surface charge density, that's just charge per square meter. So I put a charge on the sphere. And what happens, you probably know by now, is that all of that charge, all of that positive charge, is out here on the surface of the sphere. Right, on a conductor, all the charges are at the surface of the conductor. Okay, so far so good. So now what we do is, suppose magically you are able to introduce a positive charge. Did I say no, negative. Let's do a negative charge, and we're going to put it right there at the center. Suppose we introduced a negative charge right there in the center. What effect does that have? Now, what's always true that the electric field is zero in the conductor. So I mean, like in sort of the meat of the conductor, in between R1 and R2, that electric field is going to be zero. So, I mean, maybe naively you would say something like, well, if I put a charge in there, it's not, you wouldn't be able to sort of tell from the outside because that electric field being zero inside the conductor kind of swamps everything out. But here's what actually happens, and you can show this with Gauss's law. Okay. First of all, you know something interesting has to happen, because if I put that thing there, if E equals 0 in the conductor, then look at what that means. Suppose I do this. What if, I'm going to run out of colors. Let's make a little Gaussian surface out here in between R1 and R2. So let's look at the electric field at some point out there between them. Well, what happens is, what I know is that E dot dA, Gauss's law, is Q enclosed over epsilon naught, right? And so this part leads to, I'm going to have E dot 4 pi R squared, because that's the surface area, right, is Q enclosed over epsilon naught. Now, the deal is, I know that electric field at that point, at that R, in between R1 and R2, the electric field has to be zero, right? Because I'm inside the conductor. So that means, then, that this, the enclosed charge, has to be zero. But look, all that I've written so far, that enclosed charge, it looks like it's negative 0.5. Right? But it can't be true. The enclosed charge has to be zero, according to Gauss's law. So what actually happens, and if you think about it, maybe you can get this to make sense. What actually happens is that negative charge at the very center, it will attract, one way to think about it, positive charge to that inner side of the cavity. How much? Gauss's law says it will attract Q on the inner surface has to be plus 0.5, so that the total enclosed is going to be zero by my Gaussian surface that's in the middle. So that negative 0.5 is going to pull positive 0.5 worth of charge to the inner surface of that cavity, so that the total is going to be 0, right, that I enclose with anything further out than that. So that's kind of interesting. Well, where does it pull that positive charge from? It's pulling the positive charge from the total charge on the sphere, right? It doesn't come from nowhere. That positive charge has to come from somewhere. So what that means is that the total amount of charge on the outside of the sphere has now gone down a little bit. In fact, let's figure out what it is. What is the total amount of charge? The Q on the outside is just going to be the sigma on the outside times the area, right? Because sigma is just charge divided by area. So that's just going to be my 6.37 times 10 to the minus 6 times the area 4 pi times R2 squared. I think R1, let me say R1 is like 0.2, R2 is 0.25 meters. So if I plug those numbers in, this is the reason that turns out to be convenient, because if I plug those numbers in, what I get is the original charge on the outside was plus 5 microcoulombs. Okay, so what happens is that 0.5 of that has now been pulled to the inside. So after negative charge inside, Q outside is now equal to 4.5. Okay, because half of a microcoulomb, 0.5 microcoulombs, has now been pulled to that inside surface, so I have less on the outside. Okay, so I can figure out what the new charge density is. So the new sigma is just going to be 4.5 times 10 to the minus 6 divided by 4 pi times 0.25 squared. So the sigma's just gone down a little bit. So we just figure out the new charge density, and it's 5.73. Right? So we can tell from the outside that there's a negative charge that's been introduced in the middle because it's pulled some of the positive charge away from that outer surface. So from the outside, I would be able to tell. What is the electric field just outside of the surface now? The electric field outside is just going to be, let's see, Gauss's law tells us that if we're outside the sphere, it's as if all the enclosed charge were at the very center, and then it's like a point charge, right? So it's just going to be K times Q enclosed over R squared. So that's going to be 9 times 10 to the 9th. Q enclosed. Okay, so now it's the accounting trick, right? In a way, this is easy, and then in a way, it's a little bit tougher. All right, how much charge is enclosed? Well, I have minus 0.5 in the center, plus 0.5 on the outside wall, right? Those two kind of cancel out. And then I just have whatever I have left on the outside, which I just figured out was, what, 4.5 microcoulombs. So I got 4.5 times 10 to the minus 6. That's the total amount of charge enclosed over R squared, 0.25 squared. Let's see, what did I get? When I put those numbers in, what did I get? 648,000 newtons per coulomb. Okay. Originally, that was a higher number because the original charge on the outside was 5 microcoulombs. So what I'm saying is, when we put that negative charge in the center, that information, even though the electric field inside the conductor never changed, it always is 0. But when I put that negative charge in the center, that sort of information that it's there does get leaked to the outside because the electric field went down. Because I pulled some of that positive charge away from the outside. So it's sort of an interesting result that even though the electric field always remains 0 in the conductor, I can still tell what's going on in there from the outside just because the overall electric field is going to change. Yeah, that's a really neat result.